Now let us talk about the analysis of binary traits. So we just discussed the analysis of quantitative traits. Now we are going to the binary traits, and of course the major difference between these two type traits is their distribution. While for quantitative traits we usually expect some continuous distribution, and in best case scenario this would be a Gaussian distribution as presented in the panel on the left. For binary trait we usually would observe only two values. It could be yes or no, black or white, or we could easily code that as it is widely accepted as 0, 1, for example. One event is happening, for example a disease, and 0 event is not happening. It could be also usually used as coding for controls in the medical applications. So with quantitative traits, as we just considered, we normally would assume the additive linear model where the value of the outcome is the sum of three effects, the constant, which is the same for the whole population, and then the effect of the predictor, and then some random error. And this allows us to model a continuous distribution. If outcome is binary, so our y could be either 0 or 1, we can model expected probability that y is 1 using this logistic function. And the same model actually could be expressed, it's exactly the same model but on logit scale. So we say the logarithm of the ratio of probability of being 1 divided by 1 minus probability of being 1, which is the probability of being 0, is predicted by a linear term. So the above and below expression are actually exactly the same. Also, as was the case with quantitative traits, the estimates of the model parameters intercept at beta are chosen in such a way as to provide a maximal fit of the predicted to the observed data. So what about interpretation of logistic regression coefficients? You remember that with quantitative traits and linear regression, the intercept and the coefficient of regression, they all had very clear physical interpretation. While the estimates of beta and also the intercept for logistic model are provided on logistic scale, and their physical interpretation may be difficult. In some special case, however, it is possible. For example, if the predictor is binary, then you could estimate odds ratios. So now outcome and predictor are binary, right? So if we have no other covariates in the model, we could express the data as 2 by 2 table. So that would be a classical case for computations of odds ratios. So with logistic model, after you estimate beta, if the predictor is binary, you can compute the odds ratios from beta by taking its exponent of beta. And as you probably know, depending on design, odds ratios may approximate well or less well, or actually if design is population-based with no attainment on the phenotype, then you obtain relative risk. Otherwise you obtain odds ratios which may approximate the relative risk. And the relative risk is the measure how much the risk of outcome is increased when predictor x changes by 1. We are talking about binary predictor, so it's the difference between two the predictor values. To give you an example, if a population-based cohort design relating some disease to sex, and we code sex as 0 and 0 from female and 1 for male, if you obtain the estimate of beta of 0.45, then this could be translated to the odds ratio, which would be exponential of 0.45, which would be 1.49. And we're saying that was population-based cohort design, so we could translate this to the relative risk estimate, saying that the risk of the disease is increased by 1.49 times in males compared to females. So if we actually coded males as 0 and females as 1 and would obtain the same estimates, we would say that the risk is increased by 1.49 in females compared to males. So now I want you to look at this picture, and actually you have seen this picture before. I want you to tell me what are these data. If you didn't guess yet, then probably it would be helping you if I allow you to see the names on the axis. Yes, indeed, this is the data you've seen before with my example of linear model, and I was predicting sex from height, and then I thought I need to give example of predicting a binary outcome. And then I started constructing some example, and then I thought, well, actually I do have the data with binary variable, so I was already predicting height based on sex, so I can actually turn the problem other way around and try to predict sex based on height. Why not? So if I fit the logistic model to this data, which we have considered before, and we before figured out that on average, the female was taller than the male were taller than female by, I think, 12 centimeters, and mean height of female was 168. Now, if I turn the problem all the way around and I estimate a logistic regression model, then I obtain the following estimates of the regression coefficients. I obtain the estimate of intercept of minus 83.7, and the beta coefficient is 4.8. Now I want to ask you, what would be physical interpretation? So how would you relate these numbers to the data? Well, actually, it's very difficult to. It's actually very difficult to make any physical interpretation of this data, except maybe because if we had binary predictor and we have binary outcome, then we could try to translate this beta after taking exponent to odds ratios or relative risk. But now our predictor is quantitative, and therefore this 4.8 is very difficult to interpret. What we can interpret is the sign of this beta. So beta is positive, meaning that the outcome 1 are men, right? So with height increasing, the risk of being man increases. So if we put it in terms of risks. Or actually other way around, men are taller than women, the same thing we found previously, right? So again, the exact interpretation of these values from this logistic regression are very difficult. What is easy, the interpretation of the sign of the beta, and we can tell that if beta is positive, then increase in the predictor value is associated with increased risk of being 1, with increased probability of binary outcome to be 1, in our case to be a man. And while it's difficult to make a physical interpretation of these parameters, from those estimates it's very, very easy to predict, to build predictive model. So we know that according to logistic model, the probability of the value of certain individual to have value 1, in our case this is probability of being male because we code it as 1, is following the logistic model, and we know the parameters. So we just plug in the estimate of the intercept here and the estimate of the coefficient of regression here, and then based on height for every person we can predict the probability that this person is man. So these predicted values are presented as red dots on this graph, and actually result is very, if you look at this, is very intuitively clear. Now you see that the model does very good prediction in when the height is very short or just short, then the model predicts for these individuals that they are females. And this happens in the area where the range of the heights between men and women doesn't overlap anymore, right? And in the same manner, for very tall individuals, the model predicts that they are men. And again, this happens in the area where these two distributions of height between sexes do not overlap. And in the middle, where both men and women could have this height, the model doesn't do a very good job on prediction. So this is more or less it about logistic regression model, and I just want to tell a few words about analysis of genetic data with logistic regression. And basically the idea is the same as with quantitative traits. So your predictor is genotype. For example, it's a SNP with 2 alleles and 3 genotypes possible. And then you can encode different models exactly in the same manner by coding your genotypes in different ways. And the same concerns the genotypic model. What is worth mentioning as well is a test which is used very frequently in the context of analysis of binary traits in relation to genotypic data, the Armitage trend test. So what it is, it's actually very simple thing. What you do, you code your genotype using allele dose model. So you have 0 for AA, 1 for AB, and 2 for BB, and your outcome is coded as 1 and 0, 1 for cases, 0 for controls. So you have 2 random variables, so each person has a case control status 0, 1, and has either of the 3 genotypes. So what you do, you take the vectors of these 2 random variables and you compute the correlation between the two, and you square it to obtain the coefficient of determination, and then you simply compute the score test as the product of the sample size by the coefficient of determination. And this is the Armitage trend test, and as we know, it is the score test. It's distributed as chi-square with 1 degree of freedom under null, so that if you obtain the value of 3.84 or more, you can tell that p-value is 5% or less, so it would be nominally significant deviation from null model. Okay, I'm going to make a summary both for binary and quantitative traits. Few things to keep in mind. Well, from previous presentation, you should remember that one of my major points was that strength of association can be characterized in a number of ways which are essentially complementary. So when we talk about quantitative outcomes, the coefficient of regression has clear physical interpretation and allows easy prediction. This coefficient is dependent on the scale of outcome and predictor though. Then coefficients of correlation and determination, they provide measure of how neatly the outcome and the predictor go together, how visible is the relation between two variables. And for binary outcomes, the coefficient of regression allows easy prediction and sometimes can be easily interpreted. But in many cases, only the sign you can easily interpret. So does risk go with increased or decreased values of your predictors? But prediction is easy both for binary models and for quantitative models. And p-value in either model tells you how much evidence are provided by the data to rule out the hypothesis of no association.